and many of which are breakthrough papers. So I will make just one very short remark, and then we'll give the floor to Ron. So last 30 years, we witnessed a transition from a rather theoretical subject, which was approximation theory at that time, to approximation theory being involved in a lot of really practical applications. And that transition was done under Ron's leadership. So that leadership was realized in different ways. One of those he organized and led for a long time. Many people know this very well now. Industrial Mathematics Institute at the University of South Carolina, and also he organized and was an editor-in-chief of the leading approximation theory journal, which is Constructive Approximation. So I am very glad that Ron accepted our invitation to be here and to give this lecture. So Ron, you're welcome.
Thank you, Volodya. So I was instructed that the talk should be to a general audience. I see a lot of people that know a lot about this subject, so my apologies if it's not too stimulating because you know some of the material. So in numerical computation, we're given something to compute and asked to do it within a certain error tolerance, and we build algorithms to do that. And my talk is about in what sense can we look at these algorithms and decide that they're the best possible or near best possible, that nobody's going to come along in a week from now and have a better algorithm. In this discussion, I'm going to pay special attention to high-dimensional problems. Why high-dimensional? If you look at what one would consider as the more challenging areas of numerical computation these days, some of them listed here, you'll see that most of them have some high-dimensional component to them. Okay? And the general feeling in mathematics and computational mathematics is that high dimension is problematic, it's a challenge, and so I want to concentrate a little bit on that. Okay, so what is the typical setting that I'm going to be looking at? We have some function capital F here, and I take this domain only for, it doesn't matter what the domain is, but the D here is important. That's the dimensionality. I have a function of D, capital D variables, and you may think that capital D is large. And it maps it into some Banach space, but for the purpose of this talk, take the Banach space to be R. This is not the major issue in this talk. And I have some information about this function. Maybe I know it satisfies a partial differential equation, or maybe I have some data about the function, and my job is to create an approximation, which I'll denote by f hat, to f. That could be one of my challenges, to provide such an approximation. A little bit weaker challenge would be to compute some quantity of interest, Q of f. For example, a high-dimensional integral that Ian would definitely be interested in, or to find the max or the min of this function. This kind of problem occurs in control theory and design. So that could be the challenge to me. My talk is going to be almost exclusively about this first one, where I want a full approximation to f. A lot of what I say has an interpretation or even a better theory for computing quantities of interest, but I'm not going to have time to get into that. So the problems of this type cover a lot of numerical analysis, numerical PDEs, stochastic PDEs, quadrature learning, etc. So We're not talking about a narrowly focused area at all. Okay, so I say I want to formulate an idea of checking whether an algorithm is optimal or not. Now, to do that, I have to sort of set things up, right? And I need the following ingredients. First of all, we have to agree on how we're going to measure error. If I come up with this approximation to f, I have to explain in what sense it approximates f. And we have to agree that you like my interpretation of measuring error. So I view the error will be measured in some norm, and the norm is a Banach space, norm x, and so x is a function space, right? Like an LP space or a Sobolev space or some function space in which I'm measuring the error. The second thing we have to do is we have to quantify what do we know about f. Okay, this is my target function that I want to approximate. If you tell me nothing about f, I can do nothing, right? I can't guarantee any accuracy if you don't tell me additional information about f. And Bore is smiling. Why are you smiling? That's obvious, right?
Without any information.
Yeah, you can't. So the information we have about f, we incorporate in what we call model class assumptions. So this is the, what do you know about f? If you're solving a PDE, typically you have some regularity theorem for the PDE, which gives you information about f. In other contexts, like in learning, well, that's a little more nebulous. What do you really know about the underlying function that you're receiving data about? So that's it. But we need that. So model class is going to be important in this talk. The next item we need to describe is what do we mean by an algorithm and its computational cost. Now this is going to be probably the most controversial part of my talk when I get to it, whether you'll accept what I will define as a numerical algorithm or not. But that has to be done so that we know in our competition at the end of the day we're both creating the same type of objects. Finally, you have this part of the problem is that what is the access you have to f? How do you know f? How do you enter it into the computation? What do you really know about f? There are two settings that are very common. One is that you can query f. You can ask for the values of f at points or integrals or some information about f. I'll call that query. And the other one is that you're given data. Okay, somebody comes into your office and says, I have this data. I'm sure you've all had this happen to you. That somebody comes in and I have this data. What should I do? How should I approximate the function, or how should I, they usually say interpolate the data, and then I say, why do you want to interpolate? Why is it so good to preserve the values you have? But anyway, you have these settings which are more in the numerical sense, and so we need to discuss what access we have to f. In the first part of my talk, I'm not going to be concerned about this issue, but I am in the second part. So first I'll develop my way of thinking, which hopefully you'll say, hey, that's not a bad idea. And then later at the end, the last part of the talk, I'll inject this idea that I only have partial information about the function f. Okay, so let's first talk about model classes because this is very important. Classically, if you think prior to the 1970s and somebody said, what's a model class? They would always say, well, it's some smoothness assumption on the function. That the function has so many derivatives or the like, right? Typical, let's say you're approximating this function in a norm like an LP norm. Does everybody know what an LP norm is? It's the integral of the function to the p power is the norm to the 1 over p. Not everybody is an analyst, Bore. So, okay, so if you have your Banach space norm X, model class is a compact subset of X, and in this case, if X is an LP space, the typical compact sets and the typical model classes are assumptions on the smoothness of the function. How many derivatives does the function have? How nice is it? And so S is the order of smoothness, and this space WS of LP, which is called the Sobolev space, consists of all functions which have all derivatives up to order S, and all these derivatives land in or live in LP. So that's a typical model class assumption. But I want to tell you in high dimensions this is useless. Okay? It's not a useful model class. And to bring that point out, I give you a very nice simple example by Erich Novak and Henryk Wozniakowski. They say, okay, so let's suppose you want to approximate in the L infinity norm, uniform norm, and you have a function of d variables again, and think of d as large. And let me tell you, I'll give you that this function that you're trying to approximate has derivatives of all orders. It's infinitely differentiable. Not only that, all the derivatives are bounded by 1. So that's a pretty nice function, right? You would think. Now, if you look to approximate this function, you can prove that if you want to approximate it just to accuracy 1/2, that's a pretty coarse accuracy, right? Nobody would be happy with accuracy 1/2. But if you want to, you will need 2 to the d over 2 floating point operations to do this approximation. So if d is like, what did I take, 100, you'll have 10 to the 15 operations that this is going to be impossible to implement. So you have a very nice class of functions, seemingly nice, because they're smooth, but you're in high dimensions and the dimension kills you. This is commonly referred to as a curse of dimensionality. And you can't get around it. If this is all you knew about the function, you would be dead in the water. You're not going to be able to do anything. So, well, of course, we think real-world problems can be solved, so there must be something else going on. And what's going on is that we need other model classes in high dimensions. So smoothness is not the model class for high dimensions. And I don't think anybody can convincingly say, well, I know what the model classes should be in high dimensions. There are different ideas. Different people have different ideas, and here are some of them. One is the idea that the function is sparse or compressible, which means that there's some basis or dictionary, and if you write the function in an expansion in that basis or dictionary, the coefficients in that expansion go to 0 very fast. Or maybe there are only a few non-zero coefficients. Now, is that a good model class? Well, it would depend on your applications, and you would have to show that for the problem you're trying to solve, that you really have this property. I mean, it's not enough to just say, oh, I woke up this morning and I thought of a model class and write the model class down and say, oh, I can solve this model class. Well, it may be great, thank you. It kept you off the street, but it may be completely useless because no real-world problem has functions that satisfy the model class. So the issue is, is this a realistic model class? For areas like signal processing and imaging, this is a useful model class. Another type of model class would be anisotropy. And here the idea is, okay, this function is a function of a lot of variables, but they're not all equally important. It's not democracy here. Some variables are very important, some variables are not so important. So there's a hierarchy of variables, and that's represented in what we call anisotropy. Some variables are more significant than others. And then, of course, people want to capture high-dimension functions through some sort of a tensor structures where the variables are somehow intertwined through some tensors. And what is going to be important, because I'm going to touch a little bit on deep learning, is the idea of superposition. And here the idea is that although I have a function of many variables, it's a composition of functions of fewer variables in a finite composition. And this relates to Hilbert's 13th problem, but numerically seems to be the type of model class assumption which would explain deep learning, or it has to be involved in some sense in deep learning. So there's a lot of numerical analysis developed under these assumptions. If you want to justify these model classes, you have to do some work, and you have to show that they're realistic for the problem you're trying to solve, and then you also have to show they break the curse of dimensionality in some sense, right? So that'll be part of what I'm going to talk about. Okay, and now here comes maybe the crux of the talk. What are numerical algorithms? Because I want to say, this is the best I can do with a numerical algorithm. So somehow I have to tell you what a numerical algorithm means to me. Well, since we're interested in approximating a function, f, and we create this f hat, we will create this f hat by choosing some space, I claim, some space which I denote by yn, which depends on n parameters, and the function f hat that we construct will live in that space. So for example, you could say, oh, I'll use polynomials of degree, a polynomial space of degree n. And to approximate f, I'll find a polynomial in this polynomial space of degree n, or dimension n, and that'll be my approximation. But I don't want to assume that yn is a linear space necessarily. In fact, my push will be that no, it shouldn't be a linear space. Linear spaces handcuff you too much. But in any case, there is some space sitting in the background that will be used to build your numerical algorithm. And this space will depend on n parameters. And n is roughly a gauge on how complex your algorithm will be. As n gets larger and larger, you're going to have to do more computation to find this approximation, right? You all have that feeling, right? So the number of parameters is sort of the gauge that tells us the complexity of the algorithm. It would be nice if we could say that the number of parameters is exactly how many computations we need. It doesn't quite work in such a nice way. Okay, so we tend to classify algorithms as being linear or nonlinear. But what does linear and nonlinear algorithm mean? Linear algorithm means that you use the space yn, which is linear. So it's a linear space, and in this case, since it's n parameters, it would be a linear space of dimension n. So linear doesn't mean that the algorithm is a linear map. It means you used a space which is a linear space, okay, of dimension n. And nonlinear means you used a nonlinear space. And I will first say something about linear algorithms, because let's say prior again to the 70s, people basically did linear, right? The algorithms were linear, and the typical spaces were spaces of splines, finite element spaces, those some wavelet spaces, not in the 70s, but anyway, Fourier spaces, trigonometric polynomials. This was a staple of numerical analysis up to that time. So let's first talk, suppose we say, okay, we're going to use linear spaces. I just want to get out how we could decide whether we have an optimal algorithm. If we're going to use linear spaces, then we can say, okay, we fixed the space y we're going to use, let's say of a dimension n, and we would have the error in approximating f by the elements of this space. And this error is the best we could ever do in approximating f. Of course, in our numerical algorithm, we don't have full information about f, So we can't say that we're always going to be able to achieve this error, but definitely we can't do better than this error, right? And if our knowledge is that f is in this class k, then the best we could do in approximating all the functions in k would be the soup of these errors. We always take here the pessimistic viewpoint of worst case, that whatever we do, the devil's going to come along and give us the worst possible function f in this model class and test the algorithm on that guy. Okay, so this EKY would be the best we could do using this space y. And so now you would say, oh, well, let's see, I have k, but I can choose y. Let me choose y. Should I use polynomials? Should I use some other space? Fourier space? What should I use? So I open up the competition to looking at the different possible y, with the only restriction that y be a space of dimension n. If I do that, then the best space is given by what we call the Kolmogorov width of k. Namely, you look at all spaces and look at the error you get for all these spaces, and the infimum over all choices of y, that's dn of k, that's the Kolmogorov width, and that is an absolute benchmark. You can never do in a numerical algorithm better than that, right? This is it. So if you came along with an algorithm that did performed like dnk, you would say, oh, I'm done, right? I can go home, smoke a cigar, have a sherry, or vodka if you go visit Aryeh. Whiskey, yeah, but Aryeh gives you vodka.
Oh,
Well, you also have whiskey? Okay. So you would be happy and you know that you've done the job. So if you restricted your attention to linear algorithms, the Kolmogorov width of k would tell you a benchmark which you can't do better than, and hopefully you can achieve that benchmark in your given setting. But I want to tell you that, well, linear algorithms are not enough. They're not good enough. And we discovered this in the 70s when ideas like adaptivity, thresholding, sparsity, compression, all these ideas came up. And if you're not familiar with the distinction between linear and nonlinear, I'm going to spend 2 slides to try to tell you this distinction in the simplest setting possible. So what is the setting? I want to look at approximation of functions by piecewise constants. So I'm going to take a function on 0, 1, right? What can be easier? Function on, so high dimensionality out the window for this example. I have a function on 0, 1, continuous function, and I want to approximate it. And I say, oh, I'll use piecewise constants to approximate it. Of course, you may want to go to piecewise linear, quadratic, or so, but for this example, let's say piecewise constants. Now, if I'm going to use linear spaces, if that's a linear algorithm, I must fix the partition of the interval 0, 1 in advance, right? So I have this interval, and I'm going to use piecewise constants. So I have to fix the partition in advance. And as smart as we are, what would we choose? We would choose an equally spaced partition, right? Because we don't, you know, typically the space f is not biased to any end of the interval or something, so we'd use an equally spaced partition. So that would be our linear space. Be the space of piecewise constants on this partition, which is a linear space of dimension n, right? On the other hand, what would nonlinear approximation do? It would say, well, why do you partition into equally spaced intervals? Let's allow the partition to be dependent on f. Let f tell us where to partition the function. So we would allow a partition into any n intervals. We can make some small, some big, n intervals, but that particular partition could depend on f. So we would have, in this case, the nonlinear space here, sigma n, would consist of all piecewise constant functions which have n pieces, but the pieces could be arbitrary. Now that's a nonlinear space. If you add two functions from that space together, you won't get a function in that space, right? It'll be in the space sigma 2n. You'll have 2n intervals, but not n, right? So that's nonlinear space. So that's the distinction. Linear, equally spaced, nonlinear, any partition into n intervals. Now, let's see what the effect is. Now, let's say you decide on using one of these two methods, and somebody presents you a model class. If they present you the model class of lip1 functions, these are functions which satisfy this, which means their first derivative is bounded by 1. If that's your model class, then I say both linear and nonlinear, whether you use the equally spaced case or the free not case up here, you'll get the same result. You'll get accuracy 1 over n, given that you used n intervals. And so you would say, well, there was no benefit. Why did I complicate my life by doing non-uniform partitions? There was no benefit. On the other hand, if the model class that you're given is this model class, functions which are bounded variation, which in this case, if I assume they're continuous, is the same as saying that they have a derivative, and the L1 norm, the integral of absolute f prime, is less than 1, not the L infinity norm, then with equally spaced partition, you will get no accuracy, because you fix this partition, and the devil's going to come along and put all the behavior of f way at the right, and you'll never see it with your equally spaced, right? He'll push all the energy in the function over here. He'll come up with this example, or let's say here to the left, he'll put everything about f here, and you won't be very effective at approximating f, because it can go from 0 to 1 on that little interval on the left. On the other hand, nonlinear methods, you can approximate it to accuracy 1 over n. How would you do that? Well, you take here, where everything's happening, and you would put all your energy here, dividing that interval, and no division here. In other words, you would follow where f is changing, and that's how you would put down your partition. So there's a great gain in nonlinear methods. The gain is not always apparent. I remember I want to reflect a little bit. There was a guy named Mike Powell here at Cambridge. I don't know how many of you know Mike Powell. And we would talk about nonlinear methods and adaptive, and he would say to me, Ron, I know sometimes it doesn't help me, right? Okay, that's the price I pay. It doesn't help me, but sometimes I hit the jackpot. It really helps to do something nonlinear, do something adaptive. Okay, so we want to do nonlinear methods. I want to, because they have this benefit. Now, how does that reflect in my definition of what a numerical algorithm is? I claim, and this will be maybe the controversial part of the talk, I claim that all numerical methods I know that use nonlinear methods can be put into the following framework. There are two mappings, A and M. You have to learn to love A and M, okay? A, the mapping A, looks at the function and determines n numbers from this function, n pieces of information in a typically nonlinear way. For example, in this case, it would learn where to put these intervals. That's the n numbers it would learn. Then you have the second part, M, which takes the n numbers that it's learned and maps it back into some function. This part that I found this, I could have, given that I know these breakpoints and the value at these breakpoints, I could have used piecewise linear functions. I could use, you know, this is not fixed. This is the M. How you construct from the information you drew. So I claim that the nonlinear methods used in numerical analysis take this form, and the space that you use to approximate are the elements m of z, so these are functions. As z runs through Rn, when you apply m to z, you get something in x, right, in your Banach space. And this is the space of functions I'm using, and this is a nonlinear space. It's a manifold, right? It's a parameterized manifold, parameterized by Rn. Okay? All right, and if when we approximate by such a procedure, the error is given f, you draw the information a of f, you apply m, and that's your approximation to f, and there's your error. So this is my starting point in what I wanted to find nonlinear algorithms or general computational algorithms to be. Okay, so if I say, okay, that's what a nonlinear algorithm means to me, it's going to turn out I want to put more conditions on A and M, but think for now that this is all I want. Then you would look, oh, maybe did I skip? Okay. So I view all nonlinear algorithms to take this form, an A and an M, okay? But I claim you need to put some conditions on A and M in order to comply with various things. First of all, you know you can have space-filling curves, right? Space-filling manifolds. One-dimensional curves can fill all of space. To avoid that, you assume that the mappings, these mappings are continuous. If you assume the mappings are continuous, you can avoid that. But from a numerical perspective, continuity is not enough. If you're a numerical analyst, you ask for stability. You want that if you take two functions close together, after you apply A, you don't want the values to be very far apart, right? This is a lack of numerical stability. To guarantee numerical stability, I'm going to require that both A and M are Lipschitz 1 functions. Lip 1 means that you know what it means, right? Okay, so this is what I claim to be a numerical algorithm. You have these two mappings, A and M, and they're required to be Lipschitz. And if you want to be a purist, you have to assign what the Lipschitz constant will be, some gamma, okay? So I take this as my definition of algorithms. I call these admissible algorithms. Now, if I take this as the definition of admissible algorithms, I can write down a benchmark for the performance of all algorithms, all admissible algorithms, the analog of Kolmogorov widths. I would look at any given A and M and see the performance, and then I'd take the infimum over all the admissible algorithms, where n now is the number of parameters, that is, A, remember, maps into Rn. So this is a nonlinear analog of Kolmogorov widths, and this is a quantity that I claim would be the best you could achieve with a numerical algorithm, because I require numerical algorithms to have this form. You can argue with me at wine after the talk if you don't like this definition. Okay, so this delta n, this nonlinear width, would be a benchmark for numerical algorithms. If in your given problem you could achieve accuracy like delta n, you would now say, wow, I mean, didn't I do great because I achieved the best accuracy I possibly could, at least with stable numerical algorithms. Okay, but now you could say, okay, look, I mean, on and on, delta n. Who the heck knows what delta n is, right? He said this is a benchmark. Well, great, yeah. But how do you use it? Is it really a useful benchmark? And I say yes, it is. And why it is that delta n is very much like the entropy numbers of this K. And entropy numbers, which I'll get to in just a minute, are something that I feel comfortable with, and I think for a given compact set K, I have a good chance to figure out what the entropy numbers are of this model class. And here's the theorem that says that they're like epsilon n k. First of all, there are algorithms that perform like epsilon n k. You don't know what epsilon n k is yet. You will in the next slide. Second of all, there's a theorem which we call these Carroll's inequalities, which says that if an algorithm, if there are algorithms that perform like k or n to the minus r, then the epsilon, the entropy numbers must behave like n to the minus r. So in the scale of decrease like n to the minus r, this determines exactly, entropy numbers will determine best algorithm performance, okay? The entropy of k. The main point here is that delta n and epsilon n are essentially the same. This theorem, by the way, that does this is we only have this theorem for a Hilbert space. So it's a good, nice open question whether you can do it for, what you can do for a general Banach space. For a general Banach space, we always have the Carroll's inequality, but we don't have this inequality. This inequality is proved using Johnson, Linden, Strauss, and projections, random projections, and this and that. And if you're not in a Hilbert space, there are constants that depend on dimension that arise, and we don't have as good a result. Okay, whoops. So I have to tell you what the entropy numbers are, because I'm advertising and saying, oh, it's wonderful. You can now tell the best performance of a numerical algorithm by entropy numbers. So what's entropy numbers? Well, Kolmogorov entropy is a way to measure the compactness of a set. And it was introduced by Kolmogorov as sort of the deterministic analog of Shannon entropy. Shannon entropy, which is used all the time in stochastic areas, in particular in signal processing. The deterministic analog is this Kolmogorov entropy, and the easiest way to do it is to explain it is by this picture. So this is my compact set, K, and what I want to do is I want to cover K by balls. So I fix a radius of a ball, epsilon, and say how many balls do I need to cover K? So here's the picture, whoops. Okay, so here's the balls. I take the smallest covering, the smallest in terms of the number of balls, the fewest balls that will cover K of this radius epsilon. Now that number is called the covering number of K. Okay, covering, it depends on the epsilon, obviously. Smaller epsilon, you're going to need more balls. That's a covering number, and the log of that number, okay, the log of that number is called the entropy of K. Now, why do we go to entropy numbers, and what are entropy numbers? They would reverse the process a little bit. They would say, oh, I'll give you a budget of 2 to the n balls. This is what you have. I only allow you to use 2 to the 100 balls. What's the smallest epsilon you could choose and still cover? That would be epsilon n. So if you fix the number of balls to be 2 to the n, you say what's the smallest radius you can choose for the balls and still cover K, that's the entropy number of the set K. So it's a very geometric concept, and it sort of measures compactness. And notice if you have a lot of parts of your set scattered all over the place, it's going to hurt you, right? Because you're going to have to put balls everywhere to cover all these different parts. So it tells you a lot. And usually if you propose a model class to me, I feel I can figure out what the entropy is through covering, and the other thing is packing packing of sets is almost the same as covering, and so you can figure out entropy numbers. Okay. So my advertisement is to use this. So entropy, in essence, will tell you the best you can do for a numerical algorithm if you assume the numerical algorithm takes this form of mappings A and M, and these mappings are Lipschitz. Okay. Okay, that's the first part of the talk. And now I want to turn to something a little bit more numerical. As I mentioned to you, generally speaking, you know, we have to deal with the question of what do we know about F? What access do we have about F? And I told you that, you know, there are two settings that are common. One is querying and the other is data. You're given data. So I'm going to discuss each of them. So let's first talk about query algorithms. So again, I have my model class K. Think you're in high dimensions and you have this model class. You think these are the functions that I need to capture. You have this model class, and what I allow you to do, I give you a budget N, and I say you can ask questions about any function, the given function. You know, I have one function from this model class. You can ask questions about it. What does a question mean? Question means you can apply a linear functional to F. And you have N questions. Why only N? Well, because they cost you have to pay $1 for every question. So you're not infinitely rich, so you have to have a limit as how many questions you can ask. So you get to ask N questions, and then once you ask these questions, you now have all the information you're going to have about F. And then you can use that information and try to construct your approximation to F. Okay? So you have two mappings. You have this mapping A, which extracts the information. So it's like I had already talked about. You have a mapping A and you have a mapping M. A extracts the information, M constructs. However, there's a distinction between this setting and what I already talked about. And what is the distinction? There are two distinctions. One is that I'm restricting A. I'm not allowing you a general A. I'm tying your hands and saying you must use a linear map A. So this map is linear now, right? Because it's linear functionals. So that's tying your hands. On the other hand, I'm not specifying that M is Lipschitz. Why? I think you should. But traditionally, one did not, right? You make no assumptions on the reconstruction M. So this is the usual setting for query algorithms. And then you can say, well, what's the best performance? What does best performance mean? You have the set K, and you have to cleverly choose the questions to ask, where to sample, what questions to ask about. If you're thinking about what you do, your numerical integration in high dimensions, you're saying, where do I take the values of F to form my numerical quadrature? This is similar.
Take any linear algorithm, but the integral itself.
Huh? In this case, in your case, you restrict, and we do too. You restrict the dictionary of queries. Yeah, and then this is what you call standard information, blah, blah, blah. Okay, but I don't want to get into that now. That's because you have only a quantity of interest. But if you had to approximate F fully, not just compute the integral, you wouldn't have that luxury of just picking one functional to do the job. So think in terms of full approximation. Okay, so you have N functionals you can ask for the information. And the question is, what are the best ones to ask? Given the model class, what questions should you ask? And what's the best performance? Well, the best performance is something that's classically known. Ooh, go back. And it's called the Deltan width of K. And now, Bore, you want to stand up and tell everybody not to call it the Deltan width because it should be called...
First, you should correct the name.
Yes.
Well, why, you want A?
Yes.
A.
Why?
But me, it's
It's
real.
another people.
No,
another
but I've
guy.
seen both. I've seen both
guy.
A and O.
Yeah, but they're two different people.
Oh,
Yes.
you think so? I don't know about that. I've seen Deltan with an O.
No.
All right. This is the most you're going to contribute to my talk? Is this it? Is this the limit of your contribution? Okay, change O to A. You feel better? Good. Okay. Now, what I want to talk a little bit about this Deltan width as a benchmark and how it relates to my delta n. So it's different than delta n, right? Because two things that I mentioned already different. A is linear and no restrictions on m. I believe it's worth studying putting the restriction on m that it's Lipschitz, because that would match more computation. Okay, so you now say, okay, query algorithm, where should I query? Where should I query? And this depends on the model class. And what do we know? Well, I can't go through everything, but I'll tell you a little bit. We know that if you start with, well, by the way, first I give broad description of what people do in querying. What tools do they use? So there are two. One is random queries. Okay, that's a common thing people advocate. Do a random query. Just pick samples at random projections, Johnson-Lindenstrauf, blah, blah, blah. And, of course, this is what you do when you're doing your high-dimensional integration, Monte Carlo, or in compressed sensing. Compressed sensing, that whole subject was built on the idea of doing random sampling. I'll get to that a little bit more in a moment. What is this? They like me so much they want me to log in. Okay, hopefully it won't bother me again. And there are deterministic ways to query. The common ones are built on ideas like hashing in computer science, discrepancy theory. Quasi-Monte Carlo is related to discrepancy theory, and these are number theory based, and commutative algebra, and then also the idea of adaptive querying. So think of what you're trying to do and why this must be hard. You're in Rn, and n is large, right? Or Rd, you have d, a function of d variables, d is large. And you have to say, I'm going to look at my function and only evaluate it, let's say, at these points. Well, even if you wanted to put, and you have a budget n, and I say, well, n is 1,000, and if d is 30, you have 2 to the 30 quadrants. You can't even, or entons, you can't even put 1 point in each enton. So you better be very clever on where to sample. And that has to depend very much on your model class. Now we do know where to sample in some circumstances. The most heavily studied area is compressed sensing, where you take the model class that the functions you're trying to capture are sparse, or signals are sparse. And in this case, you can prove that the best sampling is to do random sampling. And Bori Kashin, who sits here, was a big contributor to this. And this was done actually in the 70s, right? When did you do your paper? 75, 70, 77. And it lay dormant for a long time. Nobody used this, right? And then all of a sudden, people said, well, wait a minute, maybe we can use this. But the problem is, it tells you where to sample, but it doesn't tell you how to decode the samples. How do you take the information you drew in these random samples and go back to create your approximation to your function? That's the key point that was left open. And Dave Donahoe and Manuel Candez and Terry Tao and all began studying how we should decode and proposed specific algorithms for this map M, the reconstruction some based on L1 minimization, and then there's also a thread of greedy algorithms, and the prominent guy here is this computer scientist at Rutgers. Okay, so in the case of sparsity, you do random samples. Now the disadvantage in the random samples is you draw the random samples and you don't know whether, the theory says, well, with high probability you have enough information to recover F to optimal accuracy. But high probability is not convincing enough in many respects, right? Because if you're a pessimist like me and you go in the doctor's office and he says, with high probability you're okay, and you say, well, wait a minute, what's that other probability where I'm not okay? And that becomes significant. Okay. There are other cases I mentioned here you can look at later where for other classes of functions in high dimension where we can tell you where to query. And we can prove theorems that maybe we can't prove that it's completely optimal yet, but we can tell you it performs well. And I mentioned them there, and I want to go further. Oh, Gerard, here you are. Ridge functions. Where's Gerard? Ah, you remember the good old days when we did that? Yeah. Okay. Now the last little topic. Data assimilation, which is, of course, now a dominant theme in the world we live. So in this case, I assume that what I know about F, you don't get to query it. You're given once and for all some data. That's it. I come in and I say, here's your data. That's it. That's all you have to work with. You have the data, you know that F is in the model class. I mean, there are situations where you have streaming data and you're getting more and more data. Okay, I'm not talking about that. You're given once and for all the data, the information. Do the best you can. So you can write down theoretically the best algorithm. So in this case, this is fixed. You had no choice in A. It was given to you, right? All you can choose is the reconstruction. What's the best way to reconstruct? Well, theoretically, I can write down the reconstruction, the best, using the null space of this measurement map, etc., etc. It's completely useless. I can write it down, I mean, mathematically, but you'll never find it. So the problem is, how do you actually implement? I shouldn't say never find it, but close to that. So how do you actually find it? This is called optimal recovery. And it was studied heavily by Charlie Michelli and Ted Rivlin in the 70s. But the main point is it gives you a benchmark for optimal performance. Now I want to view it from my viewpoint of this A and M, right? You're tired of hearing about A and M. You're going to go home and have nightmares about it. But if I think about what can I do? Now, in terms of my A and M, let's say I say, you have to give me an M that's Lipschitz. I want a stable reconstruction from the data. I'm not going to accept that you take the data, you do something, and you produce something, and I perturb the data ever so slightly and you get something different, completely different. Don't accept that. I require you to have a stable Lipschitz map. That's my delta N. So A is fixed, and you have the opportunity to choose your M, and you look for best performance. What you're going to find, of course, is you're not going to do better than my delta, and you're not going to do better than Gelfand width. Well, we have to stop and think about that, because in Gelfand I don't put any restrictions on M. But the point is that you don't have the luxury of finding the information about F, the best places to query. You're only given the data. So you have to be punished for that, right? I mean, if I give you, I have a function and I give you that it's on 0, 1, and I give you all the values here, how are you going to approximate it here? So there has to be some penalty you're paying for all this. And the penalty is the following. You look at, there is a constant mu, so that you can write the error, the best performance now. from, given the fixed data, as mu times the Gelfand width, or mu times my delta. And the question becomes, what is this mu? What is the penalty you pay? How good is the data for your model class? Because the data may not be good representation of your given model class. Well, there are ways to compute the way mu looks. I state here, usually you can get some information, maybe even compute it, from the null space of the measurement map, looking at a null space on K. Okay? So mu, this mu, is, I think, is not advertised enough in data in learning and in data acquisition circles. The fact that you have to pay a price for having bad data. And the reason they get away with this is they assume their data is given randomly, stochastically, and then they can average it out. And on average, the data is not bad, it's good, and so they get around it. But I still say there's something to be done here. And I mentioned that mu not only affects the error in this sense, but it affects the stability of M. Your ability to create a stable mapping will depend on this mu. Okay? And this is work that relates to these gentlemen who are strongly influenced by Cambridge. Shadran and Hansen are in Cambridge. He's in Oxford. Poole? Where is Poole? You know?
Poole is now in Bath.
Huh?
Poole is in Bath.
Okay. And Adcock is in Canada. Okay. So this is my last slide before I summarize. Deep learning, because everybody's interested in deep learning. I mean, I receive literally 100 papers a month on deep learning, everyone saying they have the secret to deep learning. And Googled Go beating the best Go players, or driverless cars, or whatever, okay? Artificial intelligence, deep learning. Here's a little bit of a take, my take. Of course, it's a very complex subject. This doesn't do any justice to it, but I wanted to make a couple remarks. In deep learning, one is faced with fitting data, typically classification algorithms, which are a little different than just fitting the data. But they take the form of my A and M. You design a neural network, and the A picks the parameters in the neural network. And the M says, okay, given the neural network, this is the function I generate from the neural network. So they do fit my paradigm. What I find lacking in the deep learning is we don't have a good description of the model classes for which deep networks perform well. Because you see, my whole thing was, you're given K, how does delta and K behave? How well can you do? And does this particular method of creating A and M, namely using neural nets, does it perform well? So I would like to see them produce for me model classes of functions and say, oh, here are the functions. We capture these functions. Nobody else can. All right? Also, they don't seem to emphasize the stability question. And there is an area called adversarial learning that seems to be related to this lack of stability in their algorithms. Okay, finally, to summarize, what I tried to do in this talk is to describe what I mean by a best algorithm for doing numerical computation, which involves approximating a function. I proposed a definition in terms of mappings A and M, and said that we should put restrictions on A and M. They should be Lipschitz. But I claim, or I'm proposing, that this should be the general definition of a numerical algorithm. I've shown you that if you take this definition, then there are intrinsic lower bounds on performance. You can't do better than this given my entropy. In particular situations, when you have less access to F, these lower bounds are too, they're not strong enough, you'll do worse than the lower bound, and that all has to be sorted out. Okay, that's it. Thank you so much.
Thank you very much, Ron. So, are there any questions, comments? Yeah. Or
In case when you approximate by a linear subspace, you have already that this operator is Lipschitz.
Yes. Well, no, well, not the A part, but not the reconstruction.
Yeah.
The reconstruction generally is done by a projection onto the space, and you may not have a bounded projection.
So there are some specific problems to estimate how well the process.
Yes, of course, you have Kadit's theorem that says you can always put a square root of n there and have a Lipschitz, basically a Lipschitz bound with square root of n. But yeah, there are millions of questions you can phrase, even in the linear case, but I think more interesting is the nonlinear case, and concentrating on reconstruction. For example, in compressed sensing, which now people would say, oh, okay, it's over. You know, we have this flood of papers, people writing on compressed sensing. But I don't think the decoding is still well settled. You know, you use L1 minimization or you use greedy algorithms. And what is the operation count? What is the stability of this? You know, I ask people in optimization, you know, tell me for L1 optimization, how many operations do I need to, you know, you use interior point, you do this, you do that. We know it, but I don't see the theorems there yet. But maybe they're there. Maybe I'm not smart enough to understand what they're doing.
other questions?
You're afraid to ask a question, or you didn't understand.
Conditioning comes into
Huh?
where the conditioning comes into this.
The condition of the mappings?
Yes,
Why? Or
because you can have a very, very nice formula, very small Gelfand width or whatnot,
but
but
poorly
it is so
conditioned.
unstable.
Right.
Practically.
And what I'm advertising is that one should inject stability. We should require it. It's, in Gelfand width, it's not assumed. One does not require that the mapping M is stable. And of course, if you look at what is the mapping to prove theorems on Gelfand width, it's a very unstable map. It says, you know, you search around, you do this and that. So I agree. That's one of the points of my talk. You're not pulling something over on me, are you, Aryeh? Because I remember one fellow who I won't mention his name, but I was doing research with, and he said, oh, I have this question I don't know how to solve. He gave me the question. I went home, and after a couple of days, I came up with a solution, presented to him at the board, and he was no reaction. I thought he would, hey, wonderful, hug me or something. Nothing, you know. 5 days later, he says, Ron, come into my office. I've discovered something. And then he told me the argument I had given him. Are you doing that to me, Aryeh? That's what I'm saying. We want M to be stable. We want both of these things to be stable. Right. So I would change the definition of Gelfand width. For numerical purposes, inject stability. Right?
Yeah,
Maybe it's more of a remark about this benchmark through Karl's inequality. I mean, this gives you just something in the rate, right? But sometimes the curse of dimension comes from such logarithmic terms which are log n to the d or something. For instance, if you consider classes of mixed smoothness, right? Then the curse of dimensionality has a different reason. And,
but then you don't have n to the minus r. I'm saying if you have n to the minus r,
you have n to the minus r, but you also have a term like log n.
No, n to the minus r means you have a constant times n to the minus r. It doesn't allow you to have something that depends on n and is growing in front of the n to the minus r. So you're saying I have log n to the d. You're saying I have log n to the d, n to the minus r. No, I don't allow this. I say if you have this without this,
but you make-
then it implies if you have this, then it does not necessarily break the curse of dimensionality.
Right. That's what I wanted to.
Yeah.
Because
Yeah.
there are cases.
So I agree. We agree. In fact, typically there are constants even if you don't have this, you may have c sub d. And c sub d may grow exponentially with d. So you think, oh, I'm okay, but the constant cd kills you. Yeah. Okay.
I just wanted to say that there are cases
Oh,
like
yeah.
this, for instance, those mixed smoothness classes.
Yes.
related to discrepancy.
Right.
Other questions or remarks?
Okay.
If not, let's thank the speaker again.